Good morning, all of you. Welcome to the another lecture of atomic structure. Myself, Suman Singh. So, in the last lecture, we have learned about the Heisenberg uncertainty principle. Okay, so now we will learn Schrödinger wave equation. So, before learning Schrödinger wave equation, we will see some of the terms which will help us to understand more effectively this Schrödinger wave equation. So, what we can see, the term is probability concept of electron. So when we talk about the probability concept of electron, we will compare this with Bohr atomic model and Heisenberg uncertainty principle. So according to Heisenberg uncertainty principle, what it tells that due to wave nature of electrons, we cannot describe the exact path followed by an electron in an atom at any time, right? And when we see this Bohr atomic theory, and according to Bohr atomic theory, the electrons are regarded as having fixed position of definite energy is no longer correct, right? Because this according to Bohr atomic theory, what he says that the atoms will be in a fixed position, and it will have a fixed energy, right? So but according to Heisenberg uncertainty principle, when we will compare this Bohr theory failed, okay, and there Bohr theory has failed. So in order to describe the position of an atom, the maximum that what we can do, the maximum that we can do is that we can only predict the possibility or relative chance of finding or locating an electron with a probable velocity in a particular region of space around the nucleus. Okay, that is what we can say. We can only predict where the electron is most likely to be found. Okay, and we have seen that Bohr theory considered electron as a material particle revolving around the nucleus in a circular orbit, whereas the concept of probability visualize an electron in terms of probability of its being found in a particular region of space around the nucleus. Okay, so from this Heisenberg uncertainty principle, what we can tell, we cannot find out exactly the position and energy of the electron. So we can maximum what we can do is that we can find out the probability that the electrons will be in this area or in this area, right? Like this. Okay, we can just find out the probability that where this the electron will be located. Okay, so this was the probability concept of electron. Now after that, we will see atomic orbital. Okay, so when we talk about the atomic orbital, what we can say that if a line is drawn enclosing the region where an electron to be found, okay, which is we can say that 90 to 95% of time such regions or space is called atomic orbital. Means what, we will see like this. Suppose we have this nucleus, and around this the electrons are revolving like this. Okay, so the place where the probability of, or we can say that the place or region where the electrons can be found, say 90 to 95% chances, the chances is there that in this region we will get the electrons, right? That region is called atomic orbital. Okay, or what we can conclude from there, that this atomic orbital is what, it is a three-dimensional region or space. Okay, it is a three-dimensional region or space around the nucleus. It is a three-dimensional, we can like this, it is a three-dimensional space around the nucleus, or around the nucleus of an atom, where there is a maximum probability of finding an electrons. Okay, and having a certain energy is called atomic orbital. So how we can describe atomic orbital? Atomic orbital is nothing but a three-dimensional space around the nucleus. Okay, around the nucleus, it is a three-dimensional space where the probability of finding an electron is maximum. Okay, or in other word, what we can say, in other word, an atomic orbital represent what, it represent the most probable space where the electron spend most of its time while in constant motion. Okay, So I hope you have understood what is atomic orbital. So after this atomic orbital and after knowing the concept of electron cloud, we will try to understand, or what we will try to learn more about this, okay? Or we will try to represent both this atomic orbital and electron cloud concept. So what we can conclude that each orbital, when we talk about the orbital, when we talk about this orbital, okay, when we talk about this orbital, this orbital is characterized by definite shape, size and orientation, okay, and therefore be represented diagrammatically. Means what, we can represent this orbital diagrammatically, and it this orbital has a definite shape, size and orientation, okay. In general, if you see the general representation of this orbital, so when we see the general representation, I will draw here, you can see. When we see the general orientation, general representation, it is generally represented by a shaded figure in which the intensity of the shading, okay, intensity of the shading is proportional to the probability of finding the electron in that location. Suppose we can do like this is the region, okay, and suppose I am representing this with this black dots, okay, like this black dots. So where the intensity of this shaded dot, you can see here, right? Let me make it bigger so that you can understand. Suppose this is a place, suppose this is a orbital, okay, and suppose this is what, this is the shaded portion where the probability of finding an electron is maximum. So where where the shaded portion will be more, there the in what we have, what I have said, in general represented by a shaded figure, okay, in which the intensity of shaded, this shaded from the dot line, you can see na, the intensity of this shading, or shown by this dot, will be proportional to the probability of finding the electron at that location. Means what, where the shaded, this black dot in this orbital will be more, in that place the probability of finding an electron will be maximum, okay. Once again I will mm, make you understand like this. Suppose this is a orbital, okay, this is an orbital, and the probability where this dotted line, okay, you can see that, you can, like this dotted line is there na? This dot, where this dot will be more, there you can say that the probability of finding an electron there is maximum, okay. I hope you are understanding this. You, in this diagram, it will be given in your book, in all the books it is given, you can refer to any book, okay. So such a representation is called what, electron cloud, or electron cloud or charge cloud representation, okay, of an orbit. So this was the electron cloud representation of atomic orbital. Now after that we will see the illustration concept of electron cloud, or we can say that difference between the orbit and orbital, okay. So when we talk about the difference between the orbit and orbital, when we talk about the difference between orbit and orbital, what we can say, when we talk about the orbit, orbit here, and orbitl, orbital, okay, orbit and orbital. So when we talk about this orbit is what, when we talk about this orbit, as postulated by Bohr, An orbit is a definite circular path. Okay, this orbit is what it is, a definite circular path around the nucleus in which the electrons revolve. Okay, now again, when we talk about this orbital, orbital is what as postulated by wave nature of electrons, an orbital is defined as a three-dimensional region or space around the nucleus within which the probability of finding an electron with a certain energy is maximum. Okay, now next, when we talk about this again, orbital, an orbital indicate an exact position or location of an atom, of an electron in an atom. Okay, as suggested by Bohr, you can I hope you remember when we have found out the energy or energy of an electron, or the distance between the nucleus and the electron in a Bohr atomic theory. At that time we have found out that the electrons of hydrogen is found at a distance of 0.53 Armstrong, right? If you remember that one, 0.53 Armstrong, right? So what we can say, an orbital indicate the exact position or location of an electron in an atom. But when we talk about these orbitals, an orbital does not specify the definition or exact position of electron in an atom, since the electron, due to its wave nature, cannot be found at a fixed distance from the nucleus. Okay, so I hope you are understanding the difference between this orbit and orbital. Now next, if you talk about this orbital, what we can say, there is a certain there is certainty, or we can say that there is a certainty about the momentum, or we can say that there is a certainty about the movement of electron in an orbit. But when we talk about the orbital, due to uncertainty principle as given by Heisenberg, there is no certainty about the movement of an electron in an orbital. Okay, so this was the basic difference between orbit and orbital. So now we will see Schrodinger wave equation. So Schrodinger, Erwin Schrodinger, which is called, in 1926, he has given his theory. So what was his theory? According to the Bohr concept, what we can say, according to the Neil Bohr concept, Neil Bohr concept strictly defined orbits around the nucleus was abundant when the de Broglie concept of wave nature of electron and Heisenberg uncertainty principle came into light. As we know that when this de Broglie equation, we have learned this, right? De Broglie equation in the previous class, if you remember that, if you have seen the previous lecture. So de Broglie equation, according to de Broglie equation and Heisenberg uncertainty principle, when this de Broglie wavelength or de Broglie concept and this Heisenberg uncertainty principle came into light, the Bohr concept, Bohr model, or we can say that the Bohr concept of orbits has completely failed. Okay, yet what we can say, yet this Bohr concept of the existence of stationary energy state around the nucleus was written in order to explain the atomic spectra. Okay, since it has failed, but to exactly define the atomic spectra, we have used this concept, the Bohr atomic model. Okay, now, after the failure of the atomic model, the scientists were in a search of new model. Okay, they were in the search of new model that could define or that could combine these three concept and explain the momentum or movement of electron in an atom. Okay, as we know that the Bohr theory has failed because of this Heisenberg and de Broglie wave concept. So scientists were in a search that we will give a model which will combine this three concept. Okay, and that will explain the momentum of electron in an atom. Okay, so what was the three concept? The first concept was the wave nature of electron as suggested by de Broglie. Okay, and the idea of uncertainty of position of an electron in an atom as suggested by Heisenberg uncertainty principle, and the idea of stationary energy level for the electron around the nucleus as suggested by Bohr postulate. Okay, so by taking these three concepts, scientists were in a search of giving a model that can explain the movement of an electron in an atom. So the atomic model that takes into an account the wave and particle nature of the electron is referred to as what, a wave mechanical model of atom. Okay, the atomic model that suggests, or we can say that the atomic model that takes into an account the wave and the particle nature of electron is referred to as a wave mechanical model of atom. Okay, so in 1926, Erwin Schrödinger, he has given a model. Okay, he has developed a new what we can say that he has developed a wave mechanical model of atom. Okay, and in his wave mechanical model of atom, in his model he visualized that an atoms as a the atom as a positively charged nucleus. Okay, what he Schrodinger visualized that, he visualized that atom as a positively charged nucleus surrounded by a standing or stationary electron wave. Okay, standing or stationary electron wave which extends round the nucleus in a Bohr circular orbit. Okay, so what we can say, so Erwin Schrödinger has visualized that atom is a positively charged, okay, nucleus surrounded by standing or stationary electron wave which extends round the nucleus in a Bohr circular orbit. Okay, thus what we can say, this model describe the electron as a what, three dimensional wave in the electronic field of positively charged nucleus. Okay, so Schrodinger proposed that if the electron has a wave like nature, what he says, Schrodinger, what he says that if the electron has a wave like nature, okay, it should obey the same equations of motion as all other known type of wave obey. Okay, means what he says that if whatever the wave we are seeing and whatever the characteristics, or we can say that whatever the character that wave, a normal wave is showing, this electron, if electron is a wave, if electron is a wave like nature, then it should also obey the same equation of motion as all other known type of waves obey. Okay, so on the basis of this simple idea, he describe an equation. Okay, on the basis of this simple idea, he describe he derive, or we can say that he derive an equation which describe the wave motion of an electron wave along any of the three axes, that is x axis, y axis and z axis. Okay, and that equation is called what, Schrodinger wave equation. Okay, so this equation, how it is written, you can see here, this equation is what, d2, this is called psi. Okay, this sign, what we are seeing here, this sign is called what, psi. So as you can see that d2 psi by dx square plus d2 psi by dz square, d2 psi by dy square plus 8 pi square m by h square e minus v psi. Okay, psi, it is written as psi, this sign. Okay, So this is the simple equation through which he described the wave mechanical model of atom. So in this here you can say this x, y and z are what? This x, y and z are Cartesian coordinate of the electrons. Okay, and this m is what? Here you can see m, right? This m is what? It is the mass of the electron. H, you all know, Planck constant. Okay, E is what? E is the total energy. Okay, total energy of the electron, which is kinetic energy plus potential energy. After that, this V is what? V is the potential energy of the electron, as you can see, and this psi is the wave function of the electron. Okay, so this was the Schrodinger wave equation as suggested by Erwin Schrodinger. Okay, so now when we talk about the significance of this psi or wave function has has got no physical significance. Okay, this psi has got no physical significance. Okay, but but when we talk about this psi square, okay, when we talk about this psi square, this psi square is what? It is the probability of locating an electron per unit volume. Okay, this one, when we talk about only psi, this side has does not have any physical significance. But when we talk about the psi square, okay, this psi square is the probability of locating an electron per unit volume. Okay, and when we talk about this, here what we have, our types is x, y and z are what? Coordinates of the location of electron. M is what? Mass of electron, and h is the Planck constant, E is the energy of the electron, V is the potential energy of the electron. So this equation, what we see here, this equation, this one, um, this equation, this equation are what? Are double derivatives of this psi. Okay, or we can say that double derivatives of wave function with respect to x, y and z respectively. This differentiation and integration, I hope you will learn in class 11 and 12 in maths, how you have to do this. Okay, so this was all about the Schrodinger wave equation. Now we will talk about something about this psi. Okay, so on solving the equation, what we obtain a psi or wave function term as an eigenfunction. Okay, this you have see here, you can see here it is written, right? I hope it will be written here. No, it is not written here. Okay, I will write here. So on solving this equation, when we have solved this Schrodinger wave equation, no need to solve or no need to remember this. It no one will ask you directly this equation. So I know this is a very complicated equation, as you can see here. So you know, don't no need to remember. We will use this equation so many times that you will automatically it will be you will get remembered this. Okay, or you will be memorize, you will automatically know how what we will write after that. So you have to know the concept. Okay, no need to memorize this equation. So when we solve this equation, we found that this psi psi is what? Psi or wave function are term as eigen function. Okay, eigen, eigen. Okay, eigen function. Okay, and here E is what? E is E or energy, or whatever the E or energy it is there, this energy is what? It is known as eigenvalue. Okay, eigenvalue. Okay, and through this we will get three quantum number. By with when we will solve this, we will get three quantum number, and that quantum number will be principal quantum number, azimuthal quantum number, magnetic quantum number. Okay, so this was all about Schrodinger wave equation. I hope you have understood this. So now in the next class we will learn about the quantum number. Okay, till that, thank you.